All right, we're learning about work today. Well, what is work? There it is right there. Roman numeral 1, it's a process that changes the energy of a system. So it's not the typical type of work you're used to hearing about, having to go out and work from 9 to 5 one day. Yes, that's work by the world's definition, but according to physics, it's very specifically a process that changes the energy of a system. So if I want my car to gain kinetic energy, right, the engine's got to do some work. It's got to exert a force through a displacement. Okay, and that's what we're going to find out work is mathematically in just a moment. If I want to use up the energy of my system, right, so let's say I decide to go out and do some things, then that's going to take some energy, and the energy of my system would reduce because guess what I'm doing? I'm doing work. So it is a process. It's not just a thing, it's a happening, right? That changes the energy of a system. So mathematically, that's what we're mainly going to focus on. It is the product of force and displacement. And so many things in physics so far have just been the product of two things, right? Think about F net. The net force acting on a system would be mass times acceleration. It's the product of mass and acceleration. Momentum, right? That's the product of mass and velocity. Well, here we got another, situation where it's the product of two things, force and displacement. So we would say the equation that goes with this is capital W, that's the variable for work, is equal to force times displacement. Simple as that. What's the unit of this thing? Well, the unit of force is the Newton, and the unit of displacement is the meter. So it's the Newton meter. But we have a shorter way to refer to the Newton meter, and that would be the joule. Named after James Prescott Joule, he was a British physicist who did a lot with understanding how heat is a type of energy, and he came up with the way to equate heat to energy, and doing that stuff in the Industrial Revolution, he earned the unit name for this idea of work. And guess what? The joule not only applies to work, but it also applies to energy. So this is the unit for both of these things right here. All right, let's get to Roman numeral 2. Conditions when work is not done. Conditions when work is not done. So just because you're applying a force does not mean you're doing work in the world of physics. So let me show you two cases when you're applying a force, but there's no work. The first one can be a little complicated to understand, so let's write down the first one. If the force is perpendicular to the displacement, no work is done. So let me give you a case in point of this. Let's say that I decide to pick up my computer, right? I pick up my computer and then I start carrying it around the house, right? So I got my hands like this, pretend like a computer is in my hands. Which way is the force exerted on the computer? It would be exerted upward, right? I'd be pushing up. But which way am I moving right now? I'm moving forward while my force is acting up. So there's my force and there's my forward movement. You can look at it from the side. And notice, since the force is at 90 degrees to the displacement, no work is done by that force. You are not doing work on that computer in that case. Right? So if you pick something up like this pen and I start going like this back and forth in front of the screen, I'm doing no work on the pen because the force is exerted up on the pen and the displacement is that direction. Up on the pen, displacement is that direction. 90-degree relationship between the force supporting the pen and the direction it's going, or the displacement. No work. All right. So that's the one that can be a little bit weird. I guess we could draw someone real quick to help us illustrate this point. So someone's like, let's say they have a book in their hand. I don't know, let's make it a present, right? We're in the season for present giving. Why not? If you're my wife, every day is a good day for presents. That's all I have to do with her to make her all happy. It's not, it's funny because everyone's got different ways they like to express their, yeah, I don't know, affection, love, whatever you want to call it, right? And some people it's quality time. Some people it's if you do things for me, that shows me that you care about me. For my wife, she just likes gifts, and they can be tiny little gifts. It doesn't have to be anything big. So this is me carrying a present to my wife, right? But since I'm exerting force upward on this thing, like that, and my displacement for this gift is that way, the delta x is in that direction, that 90-degree relationship means there's no work being done. Let's go to number 2. I think number 2 is a whole lot easier. I don't want to waste all this space, so maybe right here. Number 2. There must be a displacement. So let's say if there is no displacement, no work is done. So that means right now you're sitting in a chair probably, right? You're likely not standing up as you take notes. Well, you're exerting a force on that chair, right? And the force is exerting back on you from the chair called the normal force. Your gravity's pushing down, the normal force is pushing up on you. And so look at both of those forces, your gravity down, the normal force acting up. There's no work being done. Now, there's definitely forces, but you're not moving right now. So if you look at the equation, it makes a lot of sense. If there's no displacement, you call that 0. F times 0 is still 0. You have 0 work. An easier example, I think, is just you pushing on a wall. If you push on a wall, there's a wall right here, and it doesn't move. It doesn't matter how hard you push, how much you push. If it doesn't move, you did no work, okay? So there we go. So I guess I could put here to illustrate that point, F times delta X, and I could say if that's 0, F times 0 equals 0 joules. So there you go. Conditions when work is not done. Let's go to Roman numeral 3 and just jump right into a problem. And I want to show you that you could find the work of several different forces in one scenario. So Roman numeral 3, we're going to look at probably 2 or 3 example problems. Okay, boom. Let's start with something that all of us, it's a good reminder for all of us. Let's look at one of those problems where you have a box on the ground. Maybe you put some wheels on it. Now let's leave the wheels off. Take the wheels off, right? It's like ancient times before suitcases had wheels. This is a suitcase. And let's say this force is, let's make it 100 newtons. That'll work. That's our applied force. And we'll say this is a 25-degree angle. And we'll make our suitcase, I don't know, let's make it, I always go 50 kilograms. That's a bit much. Let's say 20 kilograms. That'll work. Yeah, that'll be good. And that's pretty heavy. That's like 40 pounds or something. And we'll say there's some friction too. And just to keep things a little bit easy on this problem, let's actually state what the friction is. So that way we don't have to do mu times Fn, right? At least for now, we don't have to. So I'll say the friction itself is maybe 20 newtons. Yeah, that'll work. And my question to you is this. What is the work done by each force? Because we have several forces in this picture, and I haven't even drawn all the forces yet, right? We also know there is a gravitational force right there, Fg. We know that the ground is pushing back with a normal force, Fn. And I know that you guys remember, I know that you remember, this needs to be broken into components, right? We can't leave it as this angled force. So we have this pull is made up of a little bit of right and a little bit of up. This would be called Fx, and this would be Fy. Let's just go ahead and find these right now. This is good review. This would be 100, right? The hypotenuse first times the, looks like we're adjacent to the angle, so that would be cosine 25. And this is 100 sine 25. So let's take a moment to find those. And this is 90.6 newtons. And this guy right here, 100 times the sine of 25 is 42.3 newtons. Perfect. And there you have it. We have 1, 2, 3, 4 forces, and we broke this force into 2 pieces, right? So now we can, actually, I'll stop saying stuff right there. I don't want to confuse anybody. So that's good. We have 4 distinct forces, and we broke one of them into components. So let's get into the question. Let's start with the work done by this force, okay? Now, this is why I stopped myself a second ago. If I ask you for the work done by this force, you have to be careful. Is this force doing work? If the force is perpendicular to the displacement, no work is done. Well, Mr. Heinrich, this is kind of acting this way, and it's acting up at the same time. So if that's what you're thinking, good. So we can't just look at this force and find the work. We have to look at its pieces and find the work done by each piece. And I just realized something very important. I didn't even give you guys a displacement. Let's say that we pull this suitcase for 10 meters, right? You have to have a displacement, otherwise you can't find the work, because what's work? It's force times displacement. So let's get to the point. If I ask for the work done by this force, only part of this force does work. And which part is that? The Fx. Do you see that? Because the Fx, check it out, it is acting parallel to the displacement. Look at the Fy. Does the Fy do any work? Nope. You told us that if the force is perpendicular to the displacement, that's 90 degrees right there, no work is done by it. So maybe we should start with the easiest of the two. Fy, the work of Fy is 0 joules. Because Fy perpendicular to displacement. Before I go on to any of the others, do you see some other forces that do 0 joules of work? Got them? Wouldn't it also be Fn and gravity, right? Because look, Fn is perpendicular to the displacement. Also, Fg, acting down, is perpendicular to the displacement at 90 degrees too. And by the way, this would be 20 times 9.8. We should get that handled right now so we don't have to worry about it later, which is 196. So I could go ahead and say work of Fy is 0 joules because of this. Also, and we could just say here, work of gravity, work of Fn. All of those have no work that they're doing because of that. All right. So I guess that was A, B, and C. Let's look at the other ones because we have some other forces acting, right? So let's get into the forces that are actually doing work now so we can move on to the next question. Hey, Fx is definitely doing work because it is parallel to the displacement. And off to the side, I'm going to make that note. It's a very important realization to make. Note, the force, or any force I should say, a force, must be parallel that's parallel, right, to the displacement for work to be done. For work to be done by that force. Should have made my cloud bigger. There we go. So now that I've said that, now that we have that in our notes, can you see that there's two forces doing work? Fx is parallel to the displacement, but friction is also parallel to the displacement. Yes, friction is acting in the opposite direction from the displacement, but it's still parallel. Just because you're acting opposite from doesn't mean you're not parallel to, right? You're still have a parallel relationship even if you're opposite from something. So these two forces are definitely doing work, Fx and friction. Let's find the work of Fx. So I'll go D here. Work of Fx would be as simple as this, Fx times delta x. It's just a force times a displacement. That's all work is. So we've got 90.6 newtons times 10. And all we have to do is move our decimal. So we have 906 joules of work being done by Fx. Now let's look at the work of friction. Simply friction times displacement. That's all we have to write, force times displacement. The force in this case is friction. Well, leave a space right here. Leave a space and put 20, because that's the friction, 20 newtons times 10 meters. And why do we leave a space? Because you got to call this negative work. It is negative work. And a lot of you are like, oh, okay, that makes sense, right? It's opposite from the displacement. Exactly. So we have to call the work negative. So here's where I'm going to split hairs. Here's where I'm going to get really picky. I'm not saying friction is negative. That's not what I'm saying. I'm saying the work itself is negative. So right underneath this, I'm going to write, well, let's get our answer first, right? We have negative 200 joules. Newton meter, that's a joule. And I'll put a little note to myself. I'll say, if force is opposite from displacement, that is considered negative work. Again, the work is negative. I'm not saying the force is negative, okay? And you'll hear me say that quite a few more times. Just want to make sure there's no misconceptions there. And finally, there's one more type of work we're going to find. Yes, that's all the forces. We've identified the work of each one of these forces. Notice I never really looked at the work of the 100 because the problem is the 100 is acting at an angle. So again, I had to look at the work done by its parts. It's Fx and it's Fy. If a question asked you, hey, what's the work of this force? You would say what? The work of that force is simply 906 because Fx is the only part of this force that's actually doing any work. Okay? I hope that makes sense to you. If not, make sure you ask me in class. What about this other idea, work net? Oh no, net again. Yeah, that's right, net again. What is the idea of netting something? It just means adding all of it together. That's all it means. So if I just add up all of my work, I just found my net work. So if I want to find my net income, what do? I add up the amount that I get from Lodi Unified School District, and I add up the amount that I get from my side business that I have, and I add up the amount maybe that was gifted to me over the course of the year, because, well, that'd be awesome. I don't get that much gifted money. If you want to give me some, that's fine. I'll give you my address, right? But you net all of your income, right? That's what net means. It's add it all up. So I'm going to add up all of my works. So this is just the general idea. I'm giving you a general equation. However many works you have, you just put them together. Well, what's work in this case? What was our work one? It was the work done by Fx plus the work done by friction. Those are the only works that we had that were actually done. These three forces did no work. So I just add those together. And in this case, what's the work of Fx? It's 906 joules plus a negative 200 joules. And yeah, you could just go straight to writing minus if you want to, 906 minus 200. That's fine with me. But again, I'm trying to hammer that point that this is a negative work. So we have 706 joules of net work done. So the question is, would this system accelerate? So let's get away from all the mechanics of how you find work. I'm going to ask you something like that. Will this system accelerate? Do you know why? Isn't this force greater than 20 newtons? Don't we have an unbalanced force of 90.6 minus 20 newtons? Yeah, that's right. Okay, we do have an F net. And if we have an F net, then we definitely have an acceleration. So you can make this assumption always and forever. If there is a net work, meaning this value is there, it's not zero, right? If there is some amount of net work, the system is accelerating. That sounds like a great multiple choice or true false question on the next test, right? These are the type of concepts that I'm making sure that you actually understand, so you're not just being math students, you're actually being physics students too. And now what I'm about to do next will really illustrate this point well. How else can we find work net? You don't just find work net by adding all the works. Sure, you can do that, and it worked here because we found them. We found the individual works done. But if work is equal to force times displacement, then shouldn't work net be equal to F net times displacement? Isn't that also a good idea, right? If work is just force times displacement, then work net must be F net times displacement. Well, let's find F net. That's not too hard. I just told you. It's 90.6 minus 20. 96.6 newtons minus 20 newtons times what? Times 10 meters. And look at that. It's 70.6. Isn't that 70.6 newtons times a 10 meter? Yep, which you got it. That's 706 joules of net work done. And that's pretty much the beginning of understanding work. Remember the bigger idea here, besides the fact that work is equal to force times the displacement, there are definitely conditions when work is not done. And what is work fundamentally? It's a process. It changes the energy of a system. In this system right here, this suitcase had no kinetic energy. And then I came along and I started pulling on it. I started doing some work. And guess what? It gained kinetic energy. It gained some energy and it had none before. That's what work is. There's definitely some more finer points to make, but that's good for this set of notes. Have a great day, guys. Talk to you soon.